Hey guys, in this video we'll look at multi-class classification using linear regression. I've done this video using R programming language, but I've tried to be as general as possible so people without any programming language background should still be able to follow. For this demo, I made use of these two commonly used datasets. First is the iris dataset and the second one is the MNIST dataset. So let's get started with the first dataset, the iris dataset. It's about a flower called iris. There are 3 species of iris flowers and you have to make use of linear regression to predict the species of the flower using other numerical features of the dataset. So the iris dataset contains 5 columns. First is the sepal length column, then you have the sepal width column, petal length, petal width column, and you have the species column, which is the species of the iris dataset. There are 3 species: Setosa, versicolor, and the third species is Virginica, which is not shown over here. So you have to make use of linear regression to predict the species of the iris dataset using the other 4 numerical columns. So the first 5 rows of the iris dataset is shown over here. Before we get started, we'll have a look at how linear regression works at the back end. For the same, we will predict petal length using sepal length and petal width. So in R, you can do that using this single line of code. If you execute that, you will get the coefficients beta 0, beta 1, and beta 2. With the coefficients, you can do the prediction using this simple linear equation. Now, how do we get the estimates? So a couple of good techniques are ordinary least squares and gradient descent. So in ordinary least squares, if I just click on it, it's going to open up. If you just scroll down, this is the formula for which you can calculate the estimates of the betas. So here x is the explanatory variables and y is the dependent variable. So in our case, the explanatory variables are sepal length and petal width, and y, which is the dependent variable, is petal length in our case. So we will store the explanatory variables inside x using this line, and also we'll store a new column called intercept with the value 1 in x. This is for the intercept. If I print it, you have the explanatory variables along with the intercept column, which is full of ones, and y contains the dependent variable, which is petal length in our case. And once we have stored x and y's, then we can calculate beta using the formula which we saw in Wikipedia, which is x transpose into x inverse into x transpose into y. So this line does the same: x transpose into x inverse into x transpose into y. And if you print it, you get the estimates of the beta. Now, if you compare this against the estimates which you got from the linear regression function in R, you can see that it's exactly same: minus 1.507, minus 1.507, 0.5423, 0.5423, and so on. Now, once you have the estimates, you can do the prediction for a new class using this linear equation, which we already saw. So you just substitute the betas in this linear equation, and you can estimate for a new flower with a different sepal length and a different petal width. Now, for the sake of example, I am just using the same old dataset, the training dataset itself. So I'm using the same old x. And if you execute this line, it's going to give the prediction for the first 6 training data points. So now we can represent this linear equation in this matrix form: y equal to a into beta, where a is the potential new points for which you want to do the prediction. So the above formula is written over here in R. So here, instead of new data points, we'll use the same old training data points itself. So x into beta. So this will give the prediction values of x using the new betas which we estimated. And if you see at the bottom the estimated values, you'll see the estimated values for x. Now, this is how you estimate betas and predict new values in linear regression. Now let's apply the same for classification as well. So we will see how we can do multi-class classification of iris dataset using linear regression in ordinary least squares. So I shouldn't use the word linear regression, rather I should use the word least squares. Okay. So for the same, let's look at an example where we need to predict species using petal length and petal width. So species is a categorical column. We want to predict species using two continuous columns, petal length and petal width. So let me plot the same. So x-axis is petal length, y-axis is petal width, and the color is the species. So you have sedosa over here, versicolor over here, and virginica over here. Now the drill is exactly the same. Here the explanatory variable is petal length and petal width, which will be stored in x, and y will have the dependent variable, which is the species. Okay. So here inside x, I'm storing petal length, petal width, and also the intercept, and I'm converting it into a matrix. And y is the dependent variable, which is a species. Now species is a categorical column. In other words, it's a text column. So what you do is you convert the text column into a binary class matrix, also called dummy variable. So if you just click on this, Wikipedia opens up for you. So for those who don't know what dummy variable is, you can just go through this. But on a high level, you create a matrix with columns equal to the total number of distinct classes available. So there are three distinct classes, sedosa, versicolor, and virginica. So you create a matrix with three columns. Say the first one corresponds to sedosa, second one corresponds to versicolor, and third one corresponds to virginica, for example. So you give 1 to the sedosa column for rows whose species is sedosa. So this is a binary class matrix. So this particular line of code just converts the species column into a binary class matrix and stores it into y. So once you convert it into binary class matrix, so once you convert into a binary class matrix, it looks something like this. So in this case, the first column corresponding to sedosa, the second column corresponds to versicolor, and the third column corresponds to virginica. So in the data set, the first 50 rows is sedosa data point, so that's why you can see 1 for the first 50 rows, and the next 50 rows corresponds to versicolor, but it's compressed over here, and the last 50 rows corresponds to virginica, so that's why you see 1 over here for the last 50 rows. Now once you convert it into a binary class matrix, you just apply the formula beta equal to x transpose into x inverse into x transpose into y. Now this particular line of code in R does exactly the same, just applies the formula, and you have the estimates of the betas over here, and then for a new data point you can predict the class using the same old formula, y equal to a beta. So here instead of a new data point, I'm just using the same old training data set, x into beta. So this gives me the prediction values. So here the prediction is a bit different. Now it gives you the probability that the data point belongs to a particular class. So here, for example, take the first observation. The first observation has 91% probability that it's sedosa, 21% probability that it's versicolor, and minus 13% probability that it's virginica. Ideally, probability should vary from 0 to 1. So I shouldn't be using the word probability, but still I'll use it for the ease of explanation. So ideally, the class of the new data point is the column which is maximum in value. For example, the first observation, sedosa column is maximum in value. So the first observation is sedosa. For example, this particular observation, the maximum value is the third column. So this particular observation predicted class is virginica, and so on. Okay, so the prediction is potentially the probability that it belongs to a particular class. So you have to convert these probabilities into numbers, so corresponding to the column which is maximum in number. So this particular line of code just converts that probabilities into numbers. So first observation, the first column is maximum, so it's 1 over here. The last observation, so for example this observation, the third column is maximum in value. If you just look at here, you see the third column is maximum, so that's why it's 3 over here. So it's just converted those potential probability numbers into the column numbers. Now we know that 1 is sedosa, 2 is versicolor, and 3 is virginica. So just converting this 1, 2, 3 into text over here in this particular line. So you have the predicted class over here. Now if we just compare the actuals with the predicted, we can see that over here there are 34 misclassifications and 116 values which are predicted correctly. Here you have the confusion matrix. For those who don't know what a confusion matrix is, you can just click on this link and you can see what a confusion matrix is. So it gives the actuals versus predicted count. So all the Setosa values are predicted correctly. There are a few misclassifications in versicolor and virginica. That's because if you just look at the plot, this is Setosa is far away from the other two classes, but you see there's quite a bit of overlap between versicolor and virginica, so that's why there are a few misclassifications. But keep in mind that only two columns are used for prediction. Okay, so petal length and petal width, but there are two other columns which is sepal length and sepal width. So if you use all the columns for predicting species, the accuracy will be much better than the 77% which we got over here. Okay. So how does it work in the backend? To understand the same, we'll predict species using petal length. So the drill is exactly the same. Here the explanatory variable is petal length, so we'll store that in X along with intercept. The Y is the same old binary class matrix, which is already calculated. So now we can estimate the betas using the same old formula, X transpose into X inverse into X transpose into Y. Once we do that, we have the estimates of intercept and slope for each and every class. So we have intercept and slope for Setosa, we have intercept and slope for versicolor, and we have intercept and slope for virginica. Now let's plot the explanatory variable petal length on the x-axis and the Setosa column of the binary class matrix on the y-axis. So the data points which you see at the top are the Setosa data points, and the data points which you see at the bottom are the non-Setosa data points. So the data points which belongs to versicolor and virginica. Now let's draw a line with intercept of 1.26 and the slope of minus 0.24. So this line corresponds to the estimates of Setosa. Okay, so this is how it looks like. Now if you want to predict, say for example you want to predict the species of a flower whose petal length is 8. Okay, so what you do is you take this 8 and you find where this 8 falls on this line. Okay, and that particular line's y-axis value is the probability that that data point belongs to Setosa. Okay, I shouldn't use the word probability again, but yeah. Mathematically, you can just calculate that using this linear equation. Okay, beta naught plus beta 1x. So for Setosa, the beta naught, which is the intercept, is 1.26 and the slope is minus 0.24 from here, into x is 8 over here, and you get the probability that it belongs to Setosa. Similarly, you do the same for versicolor and virginica, so you get the probabilities for all three of them, and here you can see that virginica is maximum, so the probability that this data point belongs to virginica is more. Alternatively, instead of using this linear form, you can also use this matrix form, y equal to a beta, which we already saw. So if you do that, you'll get you'll get exactly the same result, minus 0.715, which is minus 0.715 over here, 0.5626, 0.5626, and 1.15 and 1.15. Okay. You can use either of the methods. So linear regression, the prediction values vary from minus infinity to infinity. So as I had already said, these are not probabilities, but I'm using the word probability for ease of my conversation. So if you want the probability values, okay, you have to go for something called logistic regression. Is one of the ways by which you can get the probabilities. There are other algorithms as well. We will not discuss about logistic regression or other probabilistic algorithms in this video because it's beyond the scope of this video. So we saw how we can do multi-class classification using iris dataset. So we'll do the same using MNIST dataset. So MNIST dataset, has about 60,000 handwritten digits, and so we have to make use of linear regression to predict the class of the handwritten digits. So for the same, I'll make two packages to import the data. So once I import the data, so I import the data over here, and if we look at the structure of data, it has two data sets. One is the train set and another is test set. So let us look at the train set for now. Inside the train set, we have the X. So X is a three-dimensional matrix. So it has 60,000 handwritten digits, and the digits is an image with 28 cross 28 pixels. Okay, so each handwritten digit has 28 rows and 28 columns of pixels. So let's look at the first handwritten digit. So this is the first handwritten digit. Looks like this. So it's a bit hard to visualize. So let's convert this into a heat map. So if I convert this into a heat map, it looks like this. It looks like a 5. So it is a red wherever it is 0, and it is yellow wherever you have a number. And it's if this number is bigger, if it's closer to 255, the more yellow it looks. Okay, so it's this is easier to visualize. Now you have 60,000 such handwritten digits. So for calculation purpose, we have to flatten this out. So flattening this out means converting this 2 dimension into a single dimension. So you concatenate the second row with the first row, you concatenate the third row with the first row, and so on. So literally you flatten this out. So instead of having 28 cross 28, you'll just have 784 features, or 708 an array of 784 values. So this particular line of code flattens out each and every handwritten image. After flattening it out, you would have converted a 3-dimensional matrix into a 2-dimensional matrix with 60,000 rows and 784 columns. So you flatten it out and you store it in X, and you just add the intercept variable, intercept column. So once you have flattened it out, let's look at Y. So Y is stored inside the Y variable, which is the actuals. So first digit is 5, second digit is 0, third digit is 4, and so on. So we have to convert this class into a binary class matrix. So you know what a binary class matrix is. We discussed it in Iris dataset. So for this particular line of code converts the classes into a binary class matrix. And once you've converted it, looks like this. So once you created the binary class matrix, you apply the same old formula. Beta is equal to X transpose into X inverse into X transpose into Y. But the catch over here is that you can find inverse of a matrix only if its determinant is not 0. But if you just take the determinant of this section, for this case, it is 0. So you cannot actually find the inverse. So it's not invertible. So the alternative is to find something called pseudo inverse. So let me click on this link, and if I click on it, it takes me back to the same old ordinary least squares page. If you just scroll down, let me search for the word pseudo inverse. So if you just search for the word pseudo inverse, you can see this is the pseudo inverse formula over here. I just highlighted it over here. Now, so you can replace this section with the pseudo inverse. Okay, so that's written over here. So this entire formula will be simplified to this formula over here. So beta is given by X pseudo inverse of X into Y. So this particular line calculates the pseudo inverse of X. Okay, and then I multiply the pseudo inverse with Y to get the estimates of the beta. Now once I got the estimates of the beta, I can predict the class of new data points by the same old formula, Y equal to A into beta. Here A corresponds to new data points, but for the sake of demo, I'll make use of the same old training data points. So X into beta, it gives me the probabilities. So now I have to convert the probabilities into the column numbers. So this particular line does that, and this is the confusion matrix, and you can see that it has predicted correctly with 86% accuracy. Now this is the training set accuracy. Let me see how this model predicts for a new unseen data set. So for a test set accuracy, so if you remember correctly, this in the data set there are two data sets, right? So we had the training set and you had also the test set, which we didn't use for training purpose. So we'll see how the model predicts for this test set. So for the same, I am applying the same old formula, y equal to a beta. So here a corresponds to the test set, and I've applied this formula for the test set in this particular cell, and here's the confusion matrix, and you can see that the prediction accuracy is 86%. It's pretty weird to see that, you know, the test set accuracy is greater than the training set accuracy. Anyways, this is how you perform a multi-class classification using least squares. So you can access this particular node from this GitHub repository. Thanks for watching.